Hello, my name is Logan French, and I will present this poster entitled Groundwater-Lake Water Flow using Flow Characterization using Seepage Velocity Point Measurements in Unnamed Lake, Minnesota. In the past, flow between groundwater and surface water has been a challenge to quantify reliably, with very few methods developed to independently make these measurements. So, over the past several years, the Streambed Point Velocity Probe, or SBPVP, was developed. The SBPVP makes direct measurements of seepage velocity at the groundwater-surface water interface and has been used in both river and lake bed settings. Here, we explain the tool and show an application in a preliminary study of a lake in Minnesota. The SBPVP, shown in Figure 2 here, performs a mini tracer test on the body of instrument, which is cylindrical in shape. Tracers with different electrical conductivities chosen to contrast with the ambient groundwater are released at the injection port easily seen in Figure 4. The flow of the water carries the tracer across detectors, and the resulting signals are stored on a data logger. Later, the signals are matched to a breakthrough curve to estimate the seepage velocity in the sediment, either discharging to the surface water or recharging the aquifer. Unnamed Lake is a small lake near Bemidji, Minnesota, with a naturally occurring organic muck layer. In 1979, a crude oil spill, shown in blue, near Bemidji contaminated the groundwater. Since then, biodegradation has resulted in a dilute plume of oil metabolites, shown in yellow, flowing to the lake. The conventional conceptual model assumes that the groundwater enters the lake and freely interacts with the bulk lake volume, hopefully providing some level of plume attenuation by dilution. Two SBPVP transects, shown in the dashed lines in Figure 1, were conducted in 2020 and 2021 and produced unexpected results. The map view and cross-sectional views are presented in Figure 6 and 7 here, with measured velocities at each location in blue. Briefly, groundwater was found to be moving faster than expected along the base of the lake, facilitated by the muck layer, which appeared to be serving as an aquitard. In the northern transect, the accelerated velocities along the bottom of the lake were measured in almost every location sampled. Flow was generally to the northeast, consistent with flow directions determined from water level data on the western shore at the end of the lake. In the southern transect, the flow direction appeared to be to the southeast, possibly under the influences of a drainage feature of the lake that permitted water to flow to a more southerly pond. Velocities similar to those at the northern transect were measured near both shores of the southern transect, but the depth of the muck in the middle of the lake was too great to safely deploy the instrument to the mineral sediment muck interface. Instead, a velocity measurement was made in the lower half of the muck. That measurement indicated that the water was moving 1 to 2 orders of magnitude slower in the muck than at the interface and also to the southeast. From this preliminary work, a new conceptual model for the lake was developed. Figure 9. Instead of groundwater discharging and mixing with the lake volume, a large proportion of the discharging water flows in a thin layer between the lake bed and the muck layer. The layer is pressurized and supports the muck layer above. This means lower mixing rates, faster bypass, and little opportunity for plume dilution. Further work will involve more SBPVP transects and taking core samples from the muck layer for permeametry and fraction of organic carbon analysis in order to better understand its role in the flow at the groundwater-surface water interface. Thank you very much.